All right, so let's continue with our next speaker, with Gioele Zardini from the Institute for Dynamic Systems and Control in Zurich. Please go ahead.
Yeah, thank you very much. Yeah, so welcome to our presentation, a compositional sheaf-theoretic framework for event-based systems. I'm Gioele, and this is a joint work with David Spivak, Andrea Censi, and Professor Emilio Frazzoli. So I'm very happy to be here. That's actually my first applied category theory conference. And I'm happy to be here because we are the engineers. So we are the famous engineers that people talked about. And we want to bring you here this perspective of engineering. So the message we want to give you is that engineering complex systems causes pain. What do we mean by that? So my background is in robotics. And as previous speakers also were saying, the task of robot designs contains a lot of different components, which are very diverse, ranging from actuation to planning, hardware, software, control, so many different things. And this gives rise to the engineering malaise. So there are many components, they are very different. For example, they operate on different time domains, such as continuous, discrete, and event-based time. And on top of that, as engineers, we like to partition. So you will find very specific people solving specific problems with very specific methods and formalisms. And so each component is modeled in a very different way. Now, at the moment when you have to put all the components all together and to co-design the system, this causes problems because you don't have a common way of describing these systems. And so that's the pain. An example of this is these new type of sensors that arise in robotics, these event-based cameras, which basically revolutionized the way some computer vision application work. So on top, you can see the images from a standard camera observing this disk, which is rotating. And here you see what would be the output of an event-based camera. So the difference is that while on one end, the normal camera produces or measures frames at fixed timestamps, so in a synchronous way, the event-based camera only reacts to certain changes of light intensities in the observed scene. And so it outputs frames only when needed. In fact, briefly, you will see that if this disk is not moving, the event camera will not output events, whereas the normal camera does. This camera is very interesting for engineering applications because it's really low power and it outputs events at a really high rate in the order of megahertz. So as a proxy of these complicated robotics problems, we wanted to bring you the case of the heading regulation. So imagine that you have a drone, you have a camera mounted on the drone, and the drone has to regulate its heading based on the observations of the camera. So basically the body dynamics produce a pose. Each pose corresponds to a different observed scene. This can be thought of as a different light field getting to the camera, which produces some events, which are processed by a regulator or a controller, which has to produce some inputs for the drone, so some actuation inputs. And this is, although this seems easy, this already contains different components. So first of all, we have hardware and software components all together. And then we have these different time domains. So we have the body dynamics, which are usually expressed in continuous time, but then we have the event camera, which is an event-based sensor, and we have the heading regulator, which also operates in discrete time. So through this work, what we are trying to do is to find an abstraction level at which these components are all the same. And in particular, we show that behavior types are promising in this direction because we can express these signals and these components with this theory, and we can also show how we can compose these components. Of course, we are not the first people doing this. Our work is mainly based on previous works of Schulz, Spivak, and Vasilakopoulos. So to start describing the system behaviors, we need the concept of the category of continuous intervals. So to do that, we first define its translation by a function. This is a function which, given a constant a positive real, maps each positive real to its shifted by a version, right? So with this in mind, we can define the category of continuous intervals, which is the category which has as objects durations. Each duration represents a interval. And the morphisms are explained as follows. So if you have two durations, L prime and L, representing two different intervals, the morphisms are just the ways you can embed one interval into the other. So if you look on the top right picture, you see if you have an interval from 0 to L prime and another one from 0 to L, you can think of the morphism from the lower one to the upper one to be the map that describes how to embed one interval into the other. The identity morphism is then simply the translation by zero function, and the composition of morphisms is given by the sum of, so the translation by the sum of the two constants. So this is useful for us to define the int pre-sheaves. An int pre-sheaves is a functor from int op to set. So int op is the opposite category of int. So if before you were thinking about morphisms as embeddings from smaller intervals into larger ones, you can think now of morphisms as restrictions of large intervals to small ones. And set is the category of sets. So with int pre-sheaves, we can define the sections of the pre-sheaves. So with this X, and those we refer to them as behaviors. And in the picture below, those could be any one of the three curves you see plotted in different colors. So those are the length L behaviors or sections. And given such a behavior, we can describe their restriction on smaller intervals by just considering the behavior on a smaller interval, for example, from A to A plus L prime. There is also a notion of compatibility between sections or behaviors. We say that two sections are compatible if basically the end of one section is equivalent to the beginning of the other section, as you can see in the picture. And this is useful to define int sheaves. Basically, an int pre-sheaf is an int sheaf if, considering all durations and all compatible sections, there exists a unique behavior or section which contains the two original compatible sections which are glued together, basically. And so int sheaves, with this picture, seems pretty clear, help us describing these behaviors, so signals and so on. And we need now a way to describe these components. And to describe components, we need machines. So a machine given two int sheaves, A and B, an AB machine, so a machine with input A and output B, is a span in the category of int sheaves. And particularly is a span where the apex is C and you go from A to B. So this is really to be thought as input-output. And the two maps are F in and F out. An easy example for this could be the one of continuous dynamical systems. So usually you define this by having A and B Euclidean spaces, you have a state space, you have the dynamics, which are governed by certain differential equation, and then you have the readout function, which given a certain state give you an output. Now we can write this with this new language, with this new machine language. This would be a machine where on top of the span we have D, which is described by all the solutions of these differential equations. And on the bottom we have C1 of A and C1 of B being the continuously differentiable function in A and B. And now F in and F out are just the projection from the solution space to the input and output space. So once we have components, we want to be able to compose them, right? You saw in the first example that we had different components. And the way to compose machines is the following. Let's say we have two machines, one with input A, output B, the other with input B and output C. We can compose them by putting the two spans near each other, and the composition is defined by this span given by the pullback, right? So given this, I will have the composite, which is a machine from A to C, which is defined by the pullback. Now, the specifics of this work is to have a closer look at a specific behavior type, the one of event streams. So what is an event stream? Think, for example, that you have a set, a length bigger than 0, and we define a length L event stream as simply a tuple, S and A. And S is a set containing time instance, is a finite set. And A is a map that maps each time instant to a specific element of the set. take, for example, the example of a Swiss traffic light. So let's say S is a set of time instants, 20, 25, 45, and 50 seconds. And A is the set of color transitions. So in Switzerland, we have red to orange, orange to green, green to orange, and orange to red. Now A, small a, is simply the map that maps each time instant to its color transition. So there are some facts about Hve. So first of all, Hve is functorial, meaning that if we have a map that goes from A to B, we can induce a morphism in event streams that goes from event streams of A to event streams of B. And this map preserves identities and composition. In fact, what event streams are just a particular case of inch sheaves. And also we can define a strong monoidal functor. So in particular, we can define the unit of the monoidal functor to be the event stream on the empty set, and the product to be this O dot product of A and B being A plus B plus A times B. And you can interpret this as follows. Imagine that you want to put together two event streams with this product. Well, if I take this will give me a new event stream. And if I take an element of this event stream, it will be either originally an element of A or an element of B or an element of A and B, both, if both had an event at this specific time. So we are ready to define an event-based system. An event-based system is nothing else than a specific machine in which the inputs and outputs are event streams. So this is a machine, as we defined it before, with event streams of type A as input and event streams of type B as outputs. And an example of this could be the one of discrete dynamical systems. Again, A and B are sets, and we can define a discrete dynamical system with a state space S, an update function, and a readout function. And again, we can define an event-based system. So we can write the apex of the span as being time instance, inputs and states which satisfy the dynamical system equations. And then we can specify F in and F out as being, well, F in is just a projection to the input space, and F out is the composition of the readout function with any state, such that we basically get the outputs. So we have a way to write discrete dynamical systems as event-based systems. Now, we said that we can compose machines. So since an event-based system is a machine, we can compose it the same way. And we can also define the tensor product. So if we want to put, if the composition we defined before can be thought of as putting event-based systems in series, this can be thought of putting them in parallel, right? So the tensor product of two event-based systems, A, B, A prime, B prime, would be an event-based system with inputs, events of A O dot A prime and outputs B O dot B prime. So exactly how we define the monoidal product. Also, the other thing we need, or we can write, is the trace of event-based systems. So let's say we have an input A times C and an output B times C. We can define the trace to be of this event-based system to be an event-based system with input A and output B. So we are able to describe these loops. And the resulting sheaf on top of the apex is just all these the behaviors in P, such that the projections in C are green, and the F in and F out are nothing else than the projections on A and B, right? So going back, we are now ready to work with these components. But one could say, yes, but in the beginning we defined continuous streams as well. So we had this mixture of continuous stream, event-based stream, and so on. So we also need to define continuous streams. This can be defined similarly to event-based event streams. So given a topological space, we can define a continuous stream by a map. So if we have an interval of length L, we just need a map that maps each element of this interval to a element of A. And we can define also Lipschitz continuous streams, which are those streams for which the map is also Lipschitz continuous. Now, okay, we defined components, we defined behaviors, we defined how to go, how to compose these components. And now we want to know how to go from different time domains to other time domains. So how can I go from continuous to discrete? Usually I need a sampler, right? So we define a sampler to be something that starts with a continuous stream of type A and ends up as an event stream of type A. And the way it does it is the following. So we have, on top of the span, we have a clock, which is exactly what you would imagine a clock to be. So it's something that a clock with period D is something that samples time and outputs ticks, which are D-spaced, basically. So the fcont function on the left will be just a projection, or will just give you the original continuous stream, continuous stream. And fhvid will be the function which just outputs these instances of the continuous stream at the specific ticks that the clock says. But as we saw in the beginning with this event-based camera, this does not really capture such a camera. This would, for example, capture a normal camera, which is synchronous, but this wouldn't capture this event-based camera because there the sampling is asynchronous and depends on something else. And to do this, without going in the details, we need the L-level crossing sampler. So what we define here is something that goes from a Lipschitz continuous stream to an event stream. And it samples only given certain conditions. What are those conditions? Well, we can define a certain level that has to be overcome by the signal. And we have an event in the output only if this level is overcome. And that's pretty much how this event-based camera works. So the event camera I showed you before has this principle. And basically each pixel of the camera has this principle, follows this principle. And then the whole camera can be expressed as the tensor product of all the pixels, basically. So to close the gap or to close the circle, we need the way to go back, right? We need the way to go from discrete to continuous. And to do this, we define what's usually used in engineering, the so-called reconstructor or zero-order hold. And this is something that takes an event stream of type A and gives back a continuous stream of type A. Now, the working principle can be understood if one looks at the figure in the bottom right. So we have an event stream, which can be represented, a length L event stream, which can be represented by these dots here. And what we do is simply reconstructing piecewise, continuously, the signal in the most, let's say, conservative way. And this would be a reconstructor. So going back to our first picture, we had this loop where we had different components in different time domains, and we now have a name for the different signals and the different types of behaviors that we are encountering. And in particular, as I said, the event camera produces events, which can be expressed as a tensor product of the single pixels. The control produces an event stream depending on the frames, on the events it gets. The body dynamics will produce a pose, which is expressed in continuous time, and so on and so forth. So this is a way in which we can describe any components of our system. Now, the outlook for this work is the following. So in engineering, we really need to understand these many different components. And I think the previous talk gave a great exposition of these problems. And the framework which we developed allows us to put together the different components: events, clocks, continuous time. But an important point here is that this framework is purely descriptive. So we are not yet synthesizing this system. So that's what we are up to. We would love to synthesize the components, and in particular, we would love to use the theory of co-design, which we are developing in parallel, to co-design different components of the system. Just to give you an idea, the theory of co-design is about resources and functionalities, and a way in which we're thinking to do this is that each of these components I introduced you has specific properties, like it needs some computation power or takes some time before giving an input produces an output. And those things can be modeled in a co-design framework in which we want to basically design each component. And that would be it. So this is some references for the paper. And if you have questions, feel free to reach us via email. Thank you very much. I think.
Thank you, and also for being perfectly on time. So let's thank
you,
Gioele. Okay, so there were a couple of questions in the chat, but they seem to have been answered. Hudson Pepper, did you want to still ask a question?
No.
Okay.
It's answered in the chat.
All right, and Valeria?
Hi. Yeah.
Hi.
Hello, Helle.
Yeah, you would like, yeah.
My question was which kind of metric spaces we're using, because I kind of wonder if they were Cartesian, they form a Cartesian closed category. And Dave replied that they think that there's kind of traditional, normal metric spaces, and they are not Cartesian closed. So he says that that the loops are taking place in the sheaf topos, but I haven't seen the topos showing up much. Do you want to kind of comment on that?
Yes. So I think the discussion here, it's where really I had to struggle with my engineering background. But the thing is, can I wait, so now I don't have access to my slides anymore. Wait. All right, yeah. So, basically, yeah, it's a standard one. Yeah, basically, there's a whole story also, which we are not telling here, but which is interesting, is that you have also causality between in machines. And what do I mean by causality? It means that inputs affect outputs. And this is well described in Schulz, Spivak, and Vasilakopoulos paper, in which basically they describe total, deterministic, and inertial systems. And there the categories are better described. But yes, so the metric spaces, here we were just looking at this example, and this subsumes many examples in robotics, in which really these cameras work with the reals. You have some light intensities that are recorded, and if you overcome some of these levels that we showed, then you have an event. So I'm sure one could go deep in understanding where the limits of these are, but I think that for most of our applications in robotics, this would be a good way to describe the system. I don't know if I got the questions correctly. It's difficult without seeing people.
Yeah, that's fine. Thank you. I mean, I'm worried about kind of being able to make the machines sort of categories when you don't have a Cartesian closed category to begin with. So, you know, I'm worrying about what we need to give the systems as assumptions for the modeling. But that sounds good.
That's an interesting question. I'm more than happy to discuss this in offline if you want to understand a bit more.
Might be the best. Yeah, that would be cool. Thank you.
And also, I guess the answers in the chat were given by David, right? So it's a good thing to have David co-author and connected at the same time.
Indeed.
Okay, I think there is also a question from Maria Monona. Please go ahead.
Yeah, thank you. I was just wondering, because there were some references to lenses, and I was wondering if they could have like some non-simple, not trivial meaning in engineering. So like not only starting from engineering and build up a model, but also have some theoretical, completely abstract theoretical properties, and find some unexpected like application in the engineering field.
Yeah, this is actually this week at the conference, that's one of the topic I would love to learn about, because as I said, this is really descriptive, but maybe there are things that we could say about the control system or any other system based on the structure we just defined, right? So maybe there is a way, without even going in the theory of co-design, in which we can already say something about the system. And I see somebody raising the hand.
Yeah.
Yeah.
So this is a great talk, and it's fundamentally oriented by time, right? We think of the one-dimensional intervals. It's like a future and a past. But what about like partial differential equation type systems where you have multiple dimensions of spatial extent as opposed to a single dimension of temporal extent? Have you thought about those at all?
So we're running a bit out of time here. So if you can give a quick answer, that's fine. And otherwise, I would suggest that you defer the discussion to Sulep. But if you have a quick answer, then please go ahead.
No, the answer is that I thought about that, but I don't have a solution yet. So I would be more than happy to discuss this with you, and maybe you have some input.
Okay. I'll hit you up on Zula. Thank you.
Okay.
Thank you very much.
There was also a question from Jake Araujo Simon, but please, maybe you can continue it on Sulep because we need to move on. So let's thank the speaker one more time.
Thank you very much.